Hey guys, what's going on? So this time around we're going to solve the circuit using KCL and KVL, also known as Kirchoff's laws. Uh, Kirchhoff was a really smart guy a couple hundred years ago who came up with a method of applying circuit analysis by looking at the currents and voltages in a circuit. So um, Kirchhoff's current law, first one we're going to start with, also known as KCL. KCL, the methodology behind KCL, basically it says that all of the current entering a node must also be leaving the node. Or another way of thinking about it is all of the currents entering the node added up must all equal to 0. Or all of the currents leaving a node must also be equal to 0 when summed up. So if I have some node here in a circuit, and I have two legs of the circuit leaving and one entering, if this is A, this is B, and this is C, Kirchhoff's current law says that all of the current entering a node must also be leaving the node. So A is equal to B plus C. Or you can write it as negative B going the opposite direction and negative C also going the opposite direction, and you can write it as A minus B minus C equals 0. This would be summing all of the currents entering the node. This would be simply summing all of the currents, or setting all of the currents entering the node equal to the sum of all the currents leaving the node. So if we look at our circuit here, we have one node at the very middle of the circuit at the top right here, and we can first apply KCL to this node. So if you think about it, how are we going to apply KCL? Well, there's three individual branches here that interact with this node. So what I'm going to do is I'm going to sum all of the currents leaving the node. That's just my personal preference. I usually always sum the currents leaving a node. It's not incorrect to sum all the currents entering the node. You can do it either way, you'll get the same answer. So if we just sum all the currents leaving the node, we're going to have negative 6 for this current source entering here. And then if I call this arbitrarily V1, this voltage, for this node in the circuit here, which would simply be the voltage between this node and ground, which would be the same thing as I1 times 50 ohms, which is this new current I just drew here. That's going to be the next part of the circuit we're going to add. So we can do, let's see, V1 over 50, because we know through Ohm's law V is equal to IR, or the current is equal to the voltage over the resistance, and that's what we just did. We took V1 over the 50 ohm resistor. For the next part, we're going to basically do the same thing here, where we take the voltage over the resistance, or we can just write negative I0 because that's what we're trying to eventually solve. So since we're summing the currents leaving the node, that's going to be negative I0. Set all of them equal to 0. So just to recap what we did there, we summed all the currents leaving the node. Since these currents are entering the node, we assign a negative sign to them for negative passive sign convention. So we have a negative 6 plus this current leaving, which would be the voltage over the resistance. And then here, instead of worrying about this resistor and this voltage source, we're going to worry about that later. We just sum the current leaving as negative I0. Alright, so this is going to be our first equation. The second equation, we're going to use KVL, which is known as Kirchoff's voltage law, which simply says if you have a loop in the circuit and you have some voltages around the loop, you can add up all the voltages and set them equal to 0. So if I have a voltage A, a voltage B, and a voltage C, A plus B plus C is equal to 0. Now notice I didn't draw voltage sources here, because that might lead you to believe that only voltage sources can be added this way. That's not true. So any voltage in the loop is going to be a candidate for this equation. So for example, up here we have a resistor. This resistor is not a voltage source, but it still has a voltage going across it, which would be our B in this loop here. If you look at it geometrically, it would be that part of the circuit. Okay, so using Kirchoff's voltage law, we're going to add all of the voltages and set it equal to 0. So I usually go clockwise, it's just habit. So if we start clockwise, following passive sign convention, we're entering the negative terminal of the voltage source. So this is going to be negative 120 volts. And we're going to add that to the next voltage in the circuit, which is simply going to be, let's see, we're going to have I1 times 10. And then the next one is going to be, let's see, this voltage here, which is V1. Made a small mistake here. This is actually I0. And then this one is going to be, I could use I1, but since I only have two equations here, I want to stick to two unknowns. Right now I have V1 and I0, so I'd like to really stick with just two unknowns. So instead of introducing a third unknown, which would be I0, and having to write a new equation for that, I'd rather just use V1 in this circumstance. So this is going to be my second equation here. So if we solve these using substitution, you can do this one of two ways. You can do it by hand using substitution, or you can use reduced row echelon format, which is also called REF, I believe. I used this all through my circuits class. This was like the best thing I could have ever found out. I have another video that goes into detail on reduced row echelon. I highly suggest, if you are allowed to use like a TI-89 or any TI calculator, or I guess they have new calculators now, like an HP calculator that can actually do RREF and you're allowed to use it, I would highly suggest learning how to do that, because that's extremely powerful for, you know, a system of equations and a set of unknowns. So I'm just going to go by hand here and just solve, because I can do it pretty quickly. So V1 over 50, just pulling this equation down here, is equal to I0 plus 6. So V1 is equal to 50 I0 plus 6. So now I have an equation for V1. If I want to plug that into this equation here, putting the 120 on the other side and starting with the I0, I'm going to get I0 times 10 plus V1, which we already have right here. So I'm just going to add it straight in. 50 times I0 plus 6 is equal to, now remember I put the 120 on the other side, so I'll carry that through. And then I just want to solve for I0. That's what this question is asking for. We've used KCL and KVL, so we're just going to go ahead and directly solve for I0. So since I've done this before, the answer is going to reduce down to negative 3 amps. So I0 is equal to negative 3 amps. So that wasn't so bad. You know, using KVL and KCL is something that is going to be built on in future lessons and future circuits, I guess, learnings and sections. So like, for example, nodal analysis uses KCL. Mesh analysis uses KVL. So if you get these methods down pat and you get really good at KCL and KVL, the upcoming nodal analysis and mesh current techniques are just going to be a breeze to you. It's going to be super easy. As well as make sure you learn how to use a reduced or echelon format if you're allowed to. I highly suggest that. It's like a really easy and fast way to solve a system of equations and a set of unknowns. So I hope this was helpful for you guys. If you have any questions, just leave them down below. And if you have any more ideas for some more videos, I'm always looking for ideas. So just leave me a comment, and whatever you want to see, just let me know, and I'll take it into consideration. Thanks, guys.